Welcome. This example will see how to calculate shear stresses in beams. So we have here a beam simply supported 10 feet in length, subject to 1 kilopounds per foot distributed load. The beam is made up of 2 wood planks to make up a T-section. And we are already given the centroid location, C point here in the cross-section, at 1.75 inches from the top of the section. And also we're given the moment of inertia. So if we're not given these, then use your statics information and knowledge to calculate the centroid and moment of inertia, because we will need these to calculate and find the maximum shear stress in the section, and also the shear stress at the web and flange junction, or the point where the web and flange meet. So even if we're given here the section area properties, the centroid and the inertia, I still need to do statics to figure out the maximum shear force, because shear stress here is happening from shear force. Need to analyze the critical section in terms of shear forces. So it's a simple equilibrium problem here. You have two reactions at A and B, and just even from symmetry you'll find that A is equal to B, the reactions, and equal to WL over 2. So resultant here WL, and you split it between the two supports, and you end up with 5 kips force. So when you draw the shear diagram, you find that of course that the maximum shear, internal shear force, is equal to the reaction, so either close to support A or support B will be the critical sections in terms of shear. And now the question is, where is tau max? I figure out, so you start with the beam. We need to think about what is a critical section along the length of this beam, and then I figure out that it's here. Now if I cut here and look in the section, where is the this is a rectangular section for sure, but in our T section here, where would be the maximum shear stress? And from the previous video we learned that tau max is happening at the centroid of the section. Any point along the centroid of the section where y is equal to 0, we will have tau max there. So tau max is equal to V max, referring to the section that we identified, over I Q max and tau web, T web. So T web here is the thickness of the web, because we're slicing this beam at the web, which is the centroid, where the centroid is. So the problem turns out to be I have V max, I have I know the thickness of the flange here to be 1 inch. I just need to figure out here Q max. So Q max, if I draw the section, the point where tau max will be is at the neutral axis. So I will slice the beam exactly at this neutral axis. I will have the top part and the lower part of it. If I analyze the top part, the red one, it's made up of the whole flange and part of the web. And then I'm left with the rest, the other part of the web, at the other slicing half, or the bottom part of slicing here. So if I give some notations, different blocks of the areas here, A1, A2, A3, and the centroids for each. Now Q max I know is the area, the first moment of area for the part that I slice at this point. So we typically covered the top part, so Q max is equal to A1 y bar 1 plus A2 y bar 2. But interestingly here, we will know from now on that also Q max, or Q at any point where you slice, you will be able to calculate this Q either by analyzing the top part that you slice or the bottom part that you slice. So in our case here, I can calculate Q max as A1 by y bar 1 plus A2 y bar 2, or it's actually the first moment of area of the lower part, which is A3 times y bar 3. So just to clarify here the notations, so y bar means the centroid location of the first part, with respect to the neutral axis, y bar 2 is that, and then y bar 3 is this. So from the definition of centroid is where it's a point in the section where the first moment of area is equal to 0. So if I refer the first moment of area of, if I split the section into two slicing parts, the first moment of area of that slice and the first moment of area of the second slice relative to the neutral axis, if this is the true neutral axis, correct one, these first moment of areas will be equal to 0. So in our case here, it's easier to deal with just an area made up of one part, which is a simple rectangle. So I'll go with the lower slicing part, the slice part here. So A3 times y bar 3. A3 is 3.25 height times 1 inch width times the half of that height, 3.25 over 2. So I end up here with Q. Tau max is equal now then to V max, Q max over I at T web. And when you plug in the values, you will end up with tau max equal to 1.45 KSI, kilo pound per square inch. So done with part A. Now part B, I'm looking at tau at the web flange junction. So I'm looking at slicing only, not at the neutral part of the web and then the flange. I will only slice here the flange. So my part of interest of this section is the flange, the 1 inch by 4 inch flange, and the height or the distance from the neutral axis to the bottom of the flange is 0.75, because the neutral axis from the top point of the section is measured to be 1.75, and the flange is 1 inch. So if I calculate here Q web flange, kind of the flange part here, is equal to A1Y1. A1 here, from what we covered in part A, is the area of the flange, 4 inch times 1 inch, times the distance here from the neutral axis to the centroid of the flange. So 0.75 plus half of the flange thickness, 0.5. So that will give me Q WF here to be 5 inches. And then we'll be able to plug this into tau formula. And I'm deciding here that the T that I'm using is T web still, because I sliced right at the web where it meets the flange. So I'm not slicing through the flange, I'm slicing through that little hair part of the web, so I take out the flange and analyze the stresses there. And then I will end up with tau WF, the web flange junction. So I'm done with what the problem asks for, but I want to actually take that a step further and kind of have that bigger picture of what stresses are developing over the whole section. So this is what we're going to do is we'll draw a distribution of shear stresses from that V. So by importance of interest are the top point of the beam, lower point of the beam, bottom point of the beam, the neutral axis, and the point where the flange and web have that junction point. I know from basic tau formula that the top and the bottom points of the beam have 0 tau because they have 0 Q. And also from calculation, I know that tau max is at the neutral axis and tau web flange junction is equal to 1.376. And you can see that it's less than tau max, and always tau is not a linear function, unlike the flexural stresses, normal stresses for bending. The formula for tau VQ over IT will result in a parabolic distribution of stresses, so I'm connecting here with kind of a parabolic line. Now what about the flange part? So if I think about the point, so if I'm in the tau WF, I'm slicing in the web, just right where it's that junction between it and the flange. Now let's say I want to move further top with very little distance. So now I'm slicing in the flange. So now this tau flange that just be right close to tau web flange Now it's the same formula, Vmax Q WF, which is because that little distance didn't make a difference in Q or the area of that Q. But now the difference is I'm slicing in that flange, and that slicing, the width of the slicing, or T dimension, that thickness that I'm cutting through, is now equal to TF, and TF is the width of the flange. So on that, instead of slicing over that thickness of the web, now I'm slicing over that whole flange width. And if T flange is equal to 4 inches and the T web is 1 inch, this means that for the same, I can just proportionally now figure out that tau F is equal to quarter value of tau WF because of that difference in thickness. And then it will go down and diminish to 0 to the top point of the section. So this is how the shear stress is distributed here. And you can see here that maximum stresses, most of the stresses from shear stresses from shear forces in beams are developing in the web. And this is why when we design in beams, we pay clear attention to the web because we know that it's carrying most of the shear force. Flanges carry most of the stresses that resist bending, but shear forces are mostly carried by web in the web part in the beam here. So that was an example that we figure out shear stresses, the maximum shear stress, and a shear stress at any point. In this case, it's the web and flange junction in a beam. And also we learned how to draw the shear stress distribution in that beam. All right, so next videos and next part of next lesson, we'll learn about shear flow. So we see here in that section, I didn't mention that, but the web and flange are connected together with a nail. So these nails are subject to also some kind of shear, what we call shear flow. So next lesson we'll learn about shear flow and how to actually design these nails and make sure that they don't break, because if they break, they will cause a failure in that beam. All right. Thanks for watching. Take care. I will see you in future videos.